Hello, welcome to Math Contest Guides, where I share basic math contest concepts for you to be more prepared for math competitions. And these are the most basic math contest concepts for you to know in order for you to do well, because these methods can be very useful, especially in the hard questions of the math competition that you're taking. In this video, I'm going to be talking about perfect squares, and essentially, I'm pretty sure that you had to take the square root of a number in a contest. That's not uncommon, you know. And essentially, when you had to do so, I'm assuming to save time you've used a calculator. However, for contests that don't allow calculators, how are you going to, take the square root of a number? Even if the contest does allow a calculator, there are still maybe some times where just pressing that square root button may not be all that useful. So what can you do in those cases? Well, we're going to start off by talking about perfect squares, how to identify one, no matter how large it is actually, and how we can take the square root of any perfect square without even using a calculator. You can even take the square root of a non-perfect square, just that you won't have, an integer. We're going to start by talking about perfect squares, and then we'll move up to like perfect cubes and perfect powers in general. Alright, so we're going to first start off by examining these numbers that are listed up here. We're going to check if they are a perfect square or not. In order to check if an integer is a perfect square or not, always prime factorize. And prime factorization is basically breaking down a number so that you write it as a product of only prime numbers. So let's do this. I like to use this method, looks like a ladder, so that's why it's called a ladder method. Okay, so now I finished my prime factorization. So notice that 2 times 2 times 2 times 2 times 2 times 2 times 7 times 7 would give us 3136. So then let's just group all these together. How many factors of 2 are there? There are 1, 2, 3, 4, 5, 6. So this means that this is 2 to the 6, right? Write it as an exponent, and there's 2 7s, so 7 to the 2. Now what's so amazing about the exponents? They're both even. Even numbers can be divided by 2. First, is it a perfect square? Yes. Why? Because we can actually split this prime factorization up into, and then now let's regroup. We can regroup this as 2 to the 3 times 7 times 2 to the 3 times 7. Amazing. So then, actually, this is just equal to 2 to the 3 times 7 and then just squared, because this is multiplied 2 times. So then, basically, we know that 3136 is equal to 2 to the 3 times 7 all squared. So the square root is just 2 to the 3 times 7. 2 to the 3 times 7 is equal to 8 times 7, which is equal to 56. So therefore, the square root of 3136 is equal to 56. Notice how it is a perfect square, because the exponents were even, so that we could split it up like this, and then we have a perfect square. So notice that the prime factorization of the number must have all even exponents for it to be perfect square. And from there, you can get the square root. 2, 4, 2, this number. Is this a perfect square? Well, let's take the prime factorization of 2, 4, 2. So then 2, 4, 2 is just equal to, the prime factorization is 2 times 11 squared. Now, we can split this 11 squared into 11 times 11. That's nice. So we can just split it up, 2 times 11 and then times 11. But notice that as much as we can split up these two 11s so that we have a group of 2 and 11, we don't have another 2 to group with this 11. So you can't actually split it up. Therefore, 2, 4, 2 is not a perfect square. So notice that if the exponents, even if one of the exponents in the prime factorization is odd, which in this case the odd one is 1, then it's not a perfect square. However, you could still take the square root of this number, because if you take the square root of the number, so square root of 2 times 11 squared, this here is just equal to square root of 2 times square root of 11 squared, and then the result, this is just 11, so you have 11 square root of 2. It's not an integer though. So That's still a way you can take the square root of a number, though. Our next example here is 2,425. Is this a perfect square? Let's prime factorize this number. Alright, so here we've gotten the prime factorization of 2,425. So we have 2,425 is equal to 5 squared times 97. Now, in case you're wondering, okay, well, I don't know if 97's a prime number or not. Well, then don't worry, because even if 97 here wasn't a prime number, it isn't a perfect square. Therefore, we can conclude that since this only has exponent 1, we can see that 2,425, it's not a perfect square. It's not. And still, you can still take the square root of the number. It just won't be, just won't be an integer. So the square root of 2,425 is just the square root of 5 squared, which is 5, and the square root of 97. So this is multiplied. And that's our answer. 5 times the square root of 97. And there we go. But it's not a perfect square. This is a very big number. There's no way that I expect someone just to look at this number and expect to know if it's a perfect square or not. You're going to have to prime factorize. So let's do exactly that. Okay, so I am done my prime factorization. And also I should probably clarify that no calculators were used in this video. I literally manually divided. I wrote a bunch of stuff on the side, which I just erased after I was done prime factorizing. I just don't want you to see some of the weird mistakes I did. Anyways, let's go ahead and examine. Notice that how many factors of 5 are here? We have 1, 2, 3, 4, 5, 6, 7, 8. So we know that this number right over here, 390,625, this is equal to 5 to the 8. And what do you notice? We can split this up as 5 to the 4 times 5 to the 4. And here we have 5 to the 4 all squared. There we go. We see that it is indeed a perfect square. And the square root of this number is just 5 to the 4, right? So then 5 to the 4, you might want to memorize this if you haven't memorized this before, but it's 625. So 625 is the square root of this large number. Okay, let's say I give you, 242n. I gave you this expression. Now, I want you to tell me, what is the smallest value of n such that this entire expression is a perfect square? Well, what do you do as your first step? You prime factorize 242. So that would be, as we said before, 242 prime factorize is 2 times 11 squared. You can rewind the video to check. It was basically the prime factorization of this. Anyways, remember, if a number is a perfect square, then this would mean that all the exponents on the prime factors would be even. And since this 2 only has exponent 1, we need to have it to have an even exponent. Now the next greatest one would just be 2. So what can n be so that this would be 2? Well, then we can have n is equal to 2. So then when n is equal to 2, then you would get 2 to the 2, because this would be 2, and using law of exponent, you just add these exponents up. And then you have times 11 squared. This is the smallest possible value of n, such that this is a perfect square. And notice, what is the square root of this number? The square root of this number, 242 times 2, would be equal to 2 times 11 equals to 22. And there we go. If I told you to evaluate the square root of 441, how would you do this? Well, first off, always prime factorize this number. So let's go ahead and prime factorize 441. Okay, so we have our prime factorization of 441. And just as a side note, it's always helpful to remember your divisibility rules when you are doing prime factorization. Anyways, we know that 441 is equal to 3 times 3 times 7 times 7. So 441 is just equal to 3 squared times 7 squared. So what you're actually evaluating is the square root of 3 squared times 7 squared. So now notice that we just have to split this up. And notice that the square root of 3 squared is just equal to 3, and the square root of 7 squared is just 7. And there we have it. The square root of 441 is 21. As I said before, we're going to go into not just perfect squares, but perfect powers. So, as you might have probably guessed already, based on our knowledge that the exponents in the prime factorization must be even for the number to be a perfect square. If the number is a perfect cube, then the exponents in the prime factorization must be what? Must be multiples of 3. Check this out. 27 is equal to what? 3 cubed. Well, why is 27 a perfect cube? Well, it's because the exponent in the prime factorization is indeed a multiple of 3, right? 3 is a multiple of 3. So, what do we see when we take the cube root of this? Well, we're just taking the cube root of 3 to the 3. This is just equal to 3 itself. If I gave you this expression, and I told you to give me the smallest value of n, such that this is a perfect 11th power, meaning that this is equal to m to the 11 for some positive integer m, what would you do? Always write the number part of this expression as a prime factorized expression. Now, this is already prime factorized, but 8 is not prime factorized. So let's prime factorize it. We have 2 to the 2 times 8 is 2 to the 3, so that's 2 to the 3 squared times n. So then, we have exponent law. 2 times 3 is equal to 6. So we just write 6 there. So now, using law of exponent again, 6 plus 2 is 8. So we have 2 to the 8 times n. And again, we want this to be a perfect 11th power. Well, if it's a perfect 11th power, then this means that this prime factorization must only have exponents that are multiples of 11. So here we have an 8. In order for n to be a multiple, in order for n to bring this to a multiple of 11, then n can equal to 2 to the 3, because when n is equal to 2 to the 3, you have 2 to the 3, and then you just combine these exponents up, and then here you would have 2 to the 11th. And what is the 11th root of 2 to the 11? It's just 2 itself. So, I hope you see the importance of prime factorization in math contests. It is a super useful technique. Never glance over it when you're given a question that involves perfect powers. It is super useful. In fact, in general, in order for the number n to be a perfect mth power, the prime factorization of m should contain exponents that are multiples of m. So for example, the number that is equal to 2 to the 4 times 16, not 16, let's write prime factors. So 2 to the 4 times 7 to the 8 times 11 to the 16. Well, I can tell you that this number is a perfect 4th power. I don't know what value it is. I have to do the math myself, and this is a very large number. But I can tell you that this is a perfect 4th power. Why? Because all the exponents are just multiples of 4. And we can even see that if we take the 4th root of this number, the 4th root of this number would just be 2 times 2 to the 2 times 11 to the 4. That would be the 4th root of this number. In fact, this is even a perfect square because all the exponents are even. And you can do this with anything, even for perfect 100th powers. If we had the number 17 to the 300 times 23 to the 200, this is a perfect 100th power. Why? Because the exponents in the prime factorization are just multiples of 100. Right? It's even a perfect 50th power. It's even a perfect 10th power. It's a perfect square, obviously. So you can see how prime factorization is super useful in this case.